What is an IP address? We all know that. An IP address is like a phone number for our devices. It's a unique numerical identifier assigned to all things connected to a network, such as computers, smartphones, and servers. It allows them to communicate with each other. Without the IP addresses, those devices wouldn't know how to send or receive information. And we also know what an IPv4 address looks like, right? It's simple, just 4 friendly dotted decimal groupings in the range from 0 to 255. For example, 192.168.1.100. But what are the differences with the successor of IPv4, the IPv6? Its main purpose is to solve the problem with the insufficient number of IPv4 addresses. And thus IPv6 uses not 4, but 8 groups of digits. Each group has 4 digits, which are not decimal, they are hexadecimal, and the groups are not separated by dot, they are separated by colon. For example, 2607 F0D0 1002 0051 followed by 15 zeros and finally a number 4 is an IPv6 address. We have never been supposed to remember an IP address, but the reality is different. Sometimes it's easier to use them directly. 192.168.1.100 can be remembered, but how about that? To fix this, the IPv6 representation is optimized, which unfortunately does not make it more clearer for the untrained eye. As a starter, it could be shortened with some simple rules. Firstly, one or more leading zeros from any group of hexadecimal digits can be removed, which is actually done to all of the leading zeros. For example, the group 0053 is converted to 53. The group 0000 is converted to 0. Then the consecutive sections of zeros are replaced with 2 colons. But keep in mind, this may only be used once in an address, as multiple usages would render the address invalid. Let's see the application of those rules in an IPv6 address. This happens after removing all leading zeros in each group. And here's the address after omitting the consecutive sections of zeros. That is actually how the loopback address is translated to 1. Okay, yes, the IPv6 address space is massive. IPv4 uses 32 bits, allowing for 4 billion addresses. With 8 groups of 4 hex digits, IPv6 uses 128 bits, meaning we have this number of IP addresses available. I mean, come on, those are 340 million billion trillion billion IP addresses. And the default allocation of IPv6 addresses given to people from, let's say, an internet service provider is 64, meaning that the first part of the address that is called prefix and is specifying the network is half of the address. Your ISP will assign that part to you, and will simply forward all packets starting with that prefix to you. The entire second part is unique for each of your devices. Your router will be responsible for transferring the packets correspondingly to your device addresses. For a context, with a 64 prefix, the whole IPv4 address space can fit in the device allocation that your ISP gave personally to you 4 billion times. And with such 64 allocation, most people will have this number of routable IP addresses available for them at home. Now, make no mistake, a larger address space is needed and is fine. With such, there will be no need for network address translation that is commonly used in IPv4 to save addresses. That is because each device on Earth will have a globally addressable IPv6 address. Hypothetically, a smart light bulb from South Africa can connect directly to a toothbrush from London, team up and form the most diverse IoT system ever existed. There will also be no need of constant recycling of previously allocated but currently unused IP addresses. But let's estimate, there are around 8 billion people on Earth. With IPv6 addressing scheme, this makes about this number of IPs per person. Yes, each living person on Earth will need to have this number of IP addresses to fill in the whole IPv6 address space. This is not an overkill, this is way beyond overkill. And of course there are some more challenges for the ordinary person. The colon symbol is a special character used when constructing an URL. It separates the host part from the port. For example, in this URL 192.168.1.100 is the IP and 8080 is the port. But remember, in IPv6 the colon symbol is used as a separator for the groups of hex digits in the address itself. How to fix this? Maybe use dot instead or escape the colons. No, just place square brackets around the address and again after the colons and the IP shortening break every living URL parsing library and tool by ignoring the specifications once again with adding one more disallowed symbol. To put it simple, how are you going to connect to this IPv6 address at port 8443 using HTTPS protocol? This is how it will look like. And naturally, when having an IP address constructed by 32 hex characters, one should more heavily rely on DNS, as the DNS name will be more memorable. But using DNS is not always an option. There are environments without internal DNS setup. Or when at some point a firewall access control list is needed, you're still going to need to handle IP addresses. And you need a firewall access control list, because remember, all your IP addresses are now routable over the internet. How about reverse DNS lookup? Say you need to add a pointer record to your DNS config for example.net, which resolves to 142.250.187.174. To construct this DNS record, you need to reverse the order of groups in the IP address and add a fixed suffix. So your record will look like this and will point to example.net. Well, now try to do the same with your IPv6 address, which is actually this. But are all IPv6 addresses routable and accessible globally? Yes and no. You can have a private network in IPv6. It is defined with a prefix as all IPv6 networks. Everything from FC00 to FDFF is considered non-routable address space for private networks. With NAT you have one external address and a mapping to one or multiple internal ones. There is no NAT in IPv6, but there is NPT. With NPT you can transform one prefix into another. Say you have a host at a private address. Then you can add an NPT rule to transform the internal prefix into an external. This means there will be one-to-one mapping between the external and the internal addresses. But how about if you have more than one service that needs to be accessible externally? Yes, for each and every service there should be a different external IP. Respectively, there should be a proper firewall configuration that will block access to all exposed addresses and ports, and then allow only the needed specific ones. IPv6 compatible devices does not need DHCP server to set an IP address, subnet mask and gateway. A device can get an address without asking a centralized server. That is accomplished by a protocol called SLAAC. It is a capability built into the IPv6 stack of each device. To put it simple, each device generates a random 64-bit number and then sets it as the device part of its address. As an intermediate step, the device also checks if somebody else is not using the generated address by executing a multicast query, but the generated number is always 64-bit. That is why SLAAC can work only with 64-bit device IDs and respectively 64-bit prefixes. So practically, if you have a 64 prefix network, you would not be able to use SLAAC and have subnetworks within your range. A 68-bit prefix and SLAAC? No, sorry. To be fair, with IPv6 there are also a lot of improvements. The new protocol provides direct connectivity for every device, enhances the routing efficiency, optimizes packet headers, brings up multicast support, eliminates the need for NAT and DHCP, and improves the security by incorporating IPsec. IPv6 is undoubtedly the future. Well, it's the future and yet it's old enough to be allowed to drink. And IPv4 is still around. Even with the IP addresses shortage, the need for network address translation, and the slightly higher latency, it just works. And the users aren't exactly banging down the doors for IPv6, because honestly, IPv4 is like an old reliable car. Outdated, clunky and slightly annoying, but every time it gets the job done. It's time to wrap this up. Is IPv6 an overkill? Maybe, but that's the point. IPv6 is the internet's way of saying we'll never run out of addresses again. Even if it's a little awkward right now, it's also a necessary evolution. Embrace the cons, update your URLs, tools and libraries, prepare a bigger calculator, hold on tight and get ready for a future where your smart fridge has more IPs than you ever imagined. Thanks for watching. Do you already possess an IPv6 address? Please share your experience.